Today, Vasily Krylov from Harvard will give his last lecture on Higgs and Coulomb branches, geometry, and representation theory. Vasily, please.
Yeah, thank you very much, as always. Okay, so first of all, maybe just let me recall what we had last time. So last time we discussed this refined quantum Hikita conjecture, and this was some statement about the identification between what we call D module of graded traces on the left-hand side. This is something that controls graded traces on our quantized Coulomb branches, and the classical equivalent D module for the Higgs branch, equivalence cohomology.
Yeah, but you see, you spoke about Hikita conjecture like everyone was an expert in the topic. The original Hikita conjecture, if I remember, it was something
Yeah,
different.
I mentioned it really briefly. Maybe let me put it again somewhere here. The original Kikita conjecture was the following statement. Original. So on the right-hand side, you just consider cohomology of the quiver variety. Sort of Hikita's question was, okay, so we have this algebra. Can we see this? Sorry?
Algebra, sorry, it's just one quiver variety, so algebra with cohomology, which comes from cohomology structure, that's it. Yeah.
Absolutely. Yes, just with the multiplication be given by the cup product. So
Okay.
no convolution here.
Mhm.
And his question was, okay, can we see this algebra on the dual side? Of course, he was motivated by these older results by Procesi and De Concini. So the conjecture that he formulated is that this algebra is actually isomorphic to the algebra of functions on so-called schematic fixed points of the Coulomb branch under the action of this torus that always appears in our story. So these are so-called schematic fixed points. And maybe indeed, let me give you. Yeah, for the purpose of this talk, I didn't want to concentrate precisely on Hikita conjecture, rather on its applications and relations to some other parts. That's why, like, I'm emphasizing that one should like deform everything and add all of these parameters. Then we get some interesting object from representation theoretic perspective. But yeah, that's the original Hikita story, and let me maybe give you just one example, simplest possible example, namely, if our resolved quiver variety is just T star T1. This particular example is self-dual, so the Coulomb branch in this case will be just the nilpotent cone for SL2. Namely, it consists of A, B, C, such that A square plus BC is equal to 0. Like traceless matrices with 0 determinant. And the action of this torus T, with respect to which we're taking the schematic fixed points, is just the action of C star, such that T acts on A trivially. So it's like a conjugation by TT inverse. T acts on B by, I don't know, T square B. T dot C is T to the power minus 2C. And then in this case, these schematic fixed points, the left-hand side of the story, will be what? By the very definition, we should take original algebra, C of A, B, C, modular A square plus BC, and now we should kill elements that have non-zero degree. That's what it means to pass to fixed points. So we kill generators B and C. But you see, we're not killing generator A. We're only killing a square because a square is minus bc. So what we get c of a modulo a square. And definitely this is a cohomology of T star P1. So that's a very, very simple example of this story. As you see, both of these algebras have very different nature. One of them is something like purely topological, right? It only depends on the topology of our quiver variety. The other thing is like purely algebraic. It measures singularity at our fixed point, basically.
Okay.
Any other questions about this?
Just want to make sure that the T acting on A is 0.
Say it again.
T acting on A is 0 or just the fixing A?
It fixes A. Yes.
Yeah, that's okay. Thank you.
Yes, it fixes A. Or you can write that it's T to the power 0, right, times A. Okay, so right, yes, and let me recall that this object that we were considering, that was some deformation of the schematic fixed points, and it was defined as follows. So we are taking our algebra, we're taking degree 0 component of it, and then we are modeling out by the relation like this, like trace relation with additional grading added. And then we complete at 0. So now let me discuss the relation of this algebra to representation theory. And actually also it will be some specialization of this conjecture that was suggested by Nakajima, actually, after Hikito formulated his conjecture. So what happens if we take this object and now we just set z equal to 0 and we specialize to these flavor parameters. So we set x being equal, like to specialize to some flavor parameter and set h bar equal to 1. So in this case, let's see what happens with both of sides of this identification star. So on the right-hand side, we just take equivariant cohomology, we specialize them to some particular point of the Lie algebra of our torus. So by localization theorem, we get cohomology of fixed points, where by fixed points, I mean fixed points of the corresponding vector field determined by x and 1. Okay? That's what people call graded Nakajima quiver variety. And if we take the left-hand side, defined this way, and we get rid of z, so this term disappears, then we will see the following. So first of all, specializing parameter x, this flavor parameter, and specializing h bar equal to 1 just means that now we are, like previously we were considering algebra like universal enveloping, like homogeneous version of it over h bar. Now we're considering h bar equal to 1, and we have some central character that corresponds to this x. So we either denote this algebra by ax. So it's like taking universal enveloping algebra and setting Casimirs to be equal to some particular collection of numbers controlled by this parameter x. And then we mod out by some ideal, and this ideal is the following. Right? So previously we had this formula, now the second term disappears, so we just get sum of a minus eta times a eta over all characters of our torus. And I haven't told you this, but we always choose a direction. As Yen pointed out during the last talk, whenever you talk about category O or objects like this, you always choose a direction. So this direction corresponds to a choice of a co-character theta of our torus, and our condition should be that the pairing of theta with this character eta is greater than 0. So we get some algebra that is called Cartan subquotient or B algebra. So Ivan Lossev likes to call it Cartan subquotient. BLPW, they have a term B algebra. Any questions about that? So these are specializations of our objects when we set z equal to 0, basically.
Yeah, I have a question to the previous story, kind of this Hikita. So in what sense it is quantum? You refined quantum, yeah?
That's because we have these z parameters. That on the, like, that the z's on the quiver variety side correspond to this, like, degree of a curve. So you see, like, this map here. One moment. The map is given by the vertex function from H to this cohomology. And this vertex function is in integration over this modular space of quasi-maps of fixed degree.
Yeah, but probably I missed something in your previous lecture, because there is this line of work, I believe, starting from old paper by Giventhal and Kim, when they have quantum cohomology instead of usual cohomology. So they make things semi-simple, and the result says, if I remember correctly, Giventhal and Kim, that the quantum cohomology of something, in that case, it was probably maybe Grassmannian or Testarov Grassmannian, it's equal to the algebra of functions on the kind of zero level of first integrals of the Toda lattice.
Yeah. That's slightly different. So indeed, quantum cohomology appears here, quantum D module. Last time I tried to explain this. So this diagram, let me now make it a bit larger. So let's see. Yeah, let me put it this way. So the statement is that this D module of graded traces is isomorphic to the quantum D module, so quantum cohomology of MH tilde, after you do H bar equal to Q specialization, so-called. But then you can show that, so this quantum D module, by the very definition, without any specializations, it can be obtained as a quotient of this classical thing using so-called cupped vertex function. And you can substitute H bar equal to Q. So this is a homomorphism of D modules, even without substituting H bar equal to Q. But then it's always true also that there is this so-called vertex function, V. But if you are not substituting H bar equal to Q, then this vertex function will live in localized cohomology. And it will correspond to, so there is the following diagram, always. Commutative diagram, that if H bar is not equal to Q, goes to localized cohomology, and this, so in this sense, like vertex functions give you a solution of the quantum D module, because this thing is a classical D module.
Yeah, all right.
But now the statement is that for H bar equal to Q, this map is well defined without localizations. And in particular, it descends to the isomorphism between this module and this module. So in other words, you can just like simply erase this part. That's what I did like in the diagram that I wrote before. And you're just saying that there is an identification between our D module that we want to understand and functionals on which we want to understand, and something classical, and the only quantum part is here in this function, in this map, because this map is defined using quasi-maps.
Okay, right. Yeah, so yeah, you can eliminate quantum cohomology from the story, and that's what you did. Yeah.
Yes, absolutely. To see, like, because yeah, eventually that. So I mean, our goal is to describe this object in as simple terms as possible. So we're eliminating quantum D module.
Right.
Okay, right. So we have these two specializations, and then what the conjecture tells us that there should be an isomorphism between this Cartan subquotient that I denote by C of AX and cohomology of fixed points of our quiver. That's Nakajima's version of the Hikita conjecture. Again, just an isomorphism of finite dimensional algebras. Both of them are commutative. And then why this algebra is important from a representation theoretic perspective? The reason is the following. Claim irreducible objects, irreducible modules over this Cartan subquotient. Remember, it's finite dimensional algebra. So irreducible modules are just one-dimensional representations. They parameterize irreducible objects in the category O for the corresponding Coulomb branch. And that's the reason why people originally studied this B algebra. By people, I mean Braden BLPW. And how this bijection works, there is always so-called induction functor that goes from the category of modules over this Cartan subquotient to the category O. And this functor simply, it's like a Verma functor, but in this more general setting. So you start with some finite dimensional module M, like highest component of your module, and then you induce to the whole thing from the half of your algebra. So here we're using that we have a natural map from AX greater than or equal than 0 to this Cartan subquotient. And you should think about this as about like analog of Cartan, U of H, and this is some analog of U of B. And that's some analog of the definition of Verma module. And then the claim is that if you start with some one-dimensional irreducible module on the left, then you produce so-called Verma module by this construction, and then this Verma module has a unique irreducible quotient, and any reducible in category O can be obtained this way. So we get
why it's not literally the corollary of this BLPW?
again, because we are not in the conical situation, so our algebra doesn't have a non-negative
yeah, but you have some replacement.
Absolutely, yes. That's not yeah. That's basically the same argument works.
Yeah. Okay.
Okay, so what's the corollary for us of all of this? So Hikita tells us that we should have an isomorphism between these two algebras. And now let's just mod out both of them by the radical. Right, so let's kill everything sort of like non-reduced, just mod out by the radical. Then by the very definition, or what we get on the left-hand side, we just get the direct sum of, just get semi-simple algebra, and we know by what we just discussed that the number of these C's, they will be labeled by irreducible objects in our category O, right? Like summons will be labeled by irreducible objects. And what happens on the right, so we have cohomology, we mod out by the radical, so we just kill everything that is not 0 degree. So we get the direct sum of copies of C labeled by components of our graded Nakajima quiver. So in other words, we get a canonical bijection between irreducible objects in our category O and connected components of our fixed points of the quiver variety, depending on this parameter x. And know that here you already see this feature that we usually see with ordinary category O. Like if our block is regular, then the number of irreducible objects in category O is always the same, like number of elements in the while group. And that precisely corresponds to the fact that like on T star G mod B, if you take fixed points with respect to generic enough co-character, then you will get W. But if your co-character is special, then you have more fixed points, so you get less components, and the number of objects in category O becomes lower. So this function is not constant. I mean, depends on our x, and components become much complicated. Like if you take x to be non-generic. Any questions about this? Okay, so now let me give you an example of this bijection, how this works, and how to think about both sides of this story, about irreducible objects and about these components, in the case when Q is an AD quiver. So when Q is an AD quiver, and for simplicity, let me assume that X is generic, so we're sort of in this regular block, then one can show that both of these sets above are parameterized by the following thing. Let me decompose lambda into the sum of fundamental weights. And then whenever you have some fundamental weight, you can associate to it what I call B. For arbitrary lambda, you can associate to it a set B of lambda. In this case, we're considering B of lambda 1. This is a so-called GQ crystal that corresponds to the irreducible representation of GQ with highest weight lambda 1. So in other words, that's some set with some additional structure, but maybe for now what's important is that number of elements in this set is just equal to the dimension of this representation. So that's like some skeleton, some discrete analog of irreducible representation of our Lie algebra. And then both of these sets, irreducible objects and components, they will be labeled by the weight mu component in this tensor product of these crystals. Again, at the level of numbers, they will just be labeled, the number of them will be equal to the dimension of the mu weight space of the tensor product of the corresponding representations. And that follows from, like, on the quiver variety side, that's Nakajima, and on the Coulomb branch side, that's Kamnitzer, Wicks, and Jacobi. And actually, one can show that this bijection is compatible with the crystal structure that I don't want to explain. Any questions about that?
Did they consider a crystal something analogous to crystal? Those people, like,
Yes.
for
Yes, they did. So actually, the idea is, I mean, it goes back to Nakajima. So I mean, this is very classical that if you just consider cohomology of a quiver variety, equivariant, right? F cross C star H bar, equivariant of MH tilde. Then there is an action. There is an action of some Yangian of this corresponding to GQ. In particular, there is an action of the Lie algebra, GQ, U, on the direct sum of all of them, if we fix W and allow V to vary. And so what Nakajima observed, he observed that, like, if you now we can specialize to this X1, then you get cohomology of this set, and then like there is something discrete that one can associate to cohomology, namely the set of connected components. And he proved that somehow, like, the action that he defined is compatible with, like, also gives a crystal structure on the set of components.
And what the structure is in the case of quiver varieties?
Yeah, so this crystal is isomorphic to this one.
Yeah, but I mean intrinsically in terms of
Right. It comes from similarly. It comes from considering some correspondences, but then you should consider some like highest terms, like in yeah.
Okay.
So there is a way to define it geometrically. Yes.
All right. Go ahead. Yeah.
Okay, and let me give you one example that will be very important. Namely, now let's assume that mu is in the W orbit of lambda, so-called extremal situation. In terms of the quiver varieties, that just means that our Nakajima quiver variety is a point. So the right-hand side is just, you have just one component here. And this description easily tells you that in this case, in this category O, there is only one irreducible object that I will call extremal module. And let me give you one more example, namely, no assumptions on mu, but let's assume that all of these lambda i's are minuscule, like here, that appear here, are minuscule. And so lambda is a sum of minuscule weights. In this case, these crystals, B of lambda I, they are very simple. In this case, B of lambda I is just a W orbit of lambda I. All of the weights are extremal. And so we get much more concrete description of these irreducible objects. Namely, they're just labeled by all possible ways to decompose mu into the sum of mu i's, such that mu I lives in W orbit of lambda I. And how to think about generators in this category O, like standard objects or Verma modules, they can be obtained as follows. Whenever you, so irreducible objects are labeled by these decompositions, and then whenever you have such a decomposition, then you can do the following thing. You see, every building block is this extremal case. So each of these mu i's just lives in W orbit of lambda I. So now what we can do, we can take a tensor product of these extremal modules all together, and then define an action of this Coulomb branch. So that's our algebra, using the co-multiplication map that I mentioned at some point. That in general, there exists a co-multiplication map from the shifted Yangian to the tensor product of shifted by other mu's. And it's a result of Alex Weeks and collaborators that it factors through these truncations. Lambda n. So, and in this way, we get all Vierma modules in our category O glued from these building blocks coming from extremal modules. Yeah, any questions about that? So that's one important idea, that you somehow can glue generators in this category O from these smaller pieces using co-multiplication. And you see, again, the crucial thing here was that our co-multiplication, it's not compatible with mu. It's like using this co-multiplication, you can make mu like simpler in some sense. Any questions about this? Okay, so now let me explain briefly the idea of the proof of this quantum Hikita, and then we'll discuss much more concrete things related to some computations there. So let me assume that our Coulomb branch has a symplectic resolution. that on the Higgs side would correspond to the fact that the fixed points of the Higgs branch are isolated. And then we are trying to understand, to construct this identification. But now let's, instead of trying to identify these two D modules explicitly, let's try to compare some of their solutions. Namely, on this cohomology side, what we can do, we can just embed our equivariant cohomology inside the equivariant cohomology of a fixed point. And explicitly, this means that like after we compose with this surjection, we get the direct sum of concrete objects, namely these vertex functions restricted to fixed points corresponding to this mu as above, decompositions of mu into the sum, mu1 plus mu, I used n. So this is some collection of solutions of our D module on the right-hand side. And on the left-hand side, we also have a natural collection of solutions labeled by the same data. Namely, on the left-hand side, we have these Wehrmann-type modules, also labeled by these decompositions of mu because of the bijection, and we can take their traces. So they will give us maps from our D module just to like functions in all of the parameters involved in our story. And on the cohomological side, it basically like follows from the geometry that this map is an embedding. On the Coulomb branch side, this is hard, and one should prove this, but one can do this for AD quivers and conjecture that should be true in general. But after you prove that this map is an embedding, then you know that to identify these two objects is just enough to compare these collections of solutions. In other words, it's enough to show that now some particular solutions coincide with each other. One of them is a trace of this theta module that is remember, is a tensor product of some building blocks. And the other thing is the vertex function restricted to a certain particular fixed point. Any questions about this? Okay, and then using localization theorem on the Higgs side and using co-multiplication on the Coulomb side, so using this construction of these theta modules as tensor products of these building blocks, of these extremal things, one can reduce this equality to this building block case, namely when mu is in the W orbit of lambda, and when the Higgs branch is just a point. So in other words, now we want to prove that trace of this one particular extremal module, L lambda mu, is equal to the vertex function. Note that now I'm not restricting to a fixed point because the Higgs branch itself is just a point. But this vertex function is still very interesting because you remember it's defined in terms of quasi-maps to our Higgs branch. So it's actually mapped to the Stecky quotient. And so this point is open inside some non-trivial Stecky quotient. Any questions about this? Okay, and let me also mention that like these modules L lambda mu, one can also treat them as certain particular irreducible modules over the shifted Yangian. So they're also interesting from that perspective. They are unique modules over the Coulomb branch for lambda, for mu in W lambda in category O, and they're also certain particular irreducible modules over the shifted Yangian. And so now let me discuss how one can understand these extremal modules, these extremal L's. And what's so special in on the Coulomb branch side about this condition that mu lives in W orbit of lambda. So on the Higgs branch side, as we discussed, it just corresponds to our quiver to be a point. Okay, so the first question is, I mean, eventually we want to understand graded traces of these extremal modules, but let's start with characters. Because in this case, we can prove more general results, and formulas are nice. And let me put no restrictions on our quiver. Let Q be an arbitrary quiver, and mu lives in W orbit of lambda. And let me assume that we have no loops. Then this torus T, as always, it acts on our Coulomb branch Hamiltonianly. And there is only one fixed point for this torus section. And now we make the following conjecture / proposition, meaning that we can prove it in ADE types for arbitrary mu in W orbit of lambda. And the conjecture is the following, that the condition that mu lives in W orbit of lambda actually has a very natural geometric meaning from the Coulomb branch perspective. Namely, it corresponds to the fact that this point P is non-singular. And note that now it's crucial that Coulomb branches are not conical, because this MC itself will be singular. But this particular fixed point will be non-singular when mu is in W orbit of lambda. And conjecturally, in general, in ADE, this is known, and actually follows from the results of Dinakar and Alex Wicks. And we also make another conjecture that, again, we can prove in types ADE using our results with Ivan Perunov, that weights of this torus acting at the tangent space to this non-singular fixed point of the Coulomb branch are given by some very concrete formula, namely, these are all negative weights that should be real. So Q is arbitrary quiver. Real means lie in W orbit of simple roots, such that the pairing of alpha with mu is greater than 0. And this conjecture is motivated by the vertex function computations, so the computations on this dual side. Any questions about this? So maybe, yeah, let me again remind that this condition on the Higgs side, it corresponds to the Higgs branch is a point, and on the Coulomb branch side, it corresponds to the fact that this unique fixed point should be non-singular. Okay, and then we prove the following theorem, that, again, in this extremal situation, whenever conjecture above holds, for example, for Q being an ADE quiver, then like these purely geometric observations about the Coulomb branch are enough to extract a character of this module. Namely, the character of this module will be just given by the following formula. So it's like just like a half of the tangent space to this particular fixed point. Product over the same set. And the same result for ADE is proven by Kamnitzer, Kalmykov, Leralapierre, and Pinet, not published yet, again, using the geometry and our result with Perunov, and also in slightly different setting, proved by Negot, using completely different approach, using some shuffle algebras approach. Any questions about this?
So, but I forgot, your quiver is now general, yeah?
Conjecture is for general quiver. The most, like, we can prove for some quivers that are not of type ED that this formula holds, but that's for some, yeah, so we cannot prove it in general. What I want to emphasize again is that, like, eventually this is some formula for the module or a certain irreducible module over the Yangian, shifted Yangian. And I think that in some form, maybe some particular case of this conjecture was conjectured by Muhin and Jung in 2014. But as you see, like using the geometry of the Coulomb range allows you to prove this conjecture like very easily. Just reduce everything to the geometry.
Yeah, so that's nice. Yeah.
Okay, and now the next question. Okay, so we see the character of this module. Can we say something? Yeah, but we originally wanted the whole graded trace of this L. And recall that the graded trace is this functional from H to C of Z that we always treat as a functional from this D module to C of Z. And now, again, we see that this extremal situation to which we reduced everything is very special. Namely, we have this D module, and we know that our graded trace, again, by formal reason, is a functional on this thing. But now let's understand this D module. Let's again specialize everything. Let's set Z equal to 0, H bar equal to 0. Then, as we discussed, what we will get something purely classical, nothing quantum. We will just get functions on the schematic fixed points of the torus acting on this MC. And you remember that, again, in type ADE, it is true, and in general, we conjecture that this point is non-singular. So in this particular case, these schematic fixed points, they will just give us complex numbers. So there will be nothing reduced, non-reduced. So then it just formally follows from some version of Nakayama lemma that the whole D module that we are considering in this case is just C of Z. And what this means, so this means that any homomorphism of D modules that satisfies this twisted trace property, namely that factors through this quotient, must be equal to the trace of a module we're looking for up to a constant. So in other words, again, we don't really need to carefully study representation theory here, this particular module. We just know from the general, from the geometry of our Coulomb range that arbitrary functional that is a homomorphism of this guy would work and would give us our trace. Okay, any questions about this? Okay, so there remains to construct some T, some solution. And I don't know how to do this for arbitrary mu in W lambda at the moment. But for our purposes, it's enough to consider the following mu. So let me give you a definition. Mu is called almost dominant, and in more like combinatorial literature, it's called predominant if the pairing of mu with alpha is greater than or equal than -1 for any alpha being real positive root. Maybe what is important for now is if lambda is minuscule, then arbitrary mu in double orbit of lambda works. So these guys to which we want to restrict for Hikita, all of them have this property. And then something interesting happens. Namely, we prove the following theorem using like completely different somehow approach. Namely, let me recall that our H is equivariant cohomology of a point. So we can think about it as a subalgebra inside functions in xij, where I are labeled by vertices of our quiver and j are from 1 to vi. So just like this is just the algebra of partially symmetric polynomials. And then we prove the following theorem, again, conjecture/theorem for IADE, that's a theorem. We conjecture that should be true for arbitrary quiver when mu is almost dominant in the sense as above, that this trace of our module is always given by certain integral over the real part of the torus for the gauge group. And what like I will explain this integral in a second, but what is written here is so-called sphere partition function of our theory that was predicted to exist and to be given by this formula by Gayota and Okazaki. Again, Gayota and Okazaki, they never thought about these extremal modules on anything, but they explained that from some physics predictions, there should be a functional that satisfies this twisted trace property, and that is given by the following formula being restricted to Cartan. That is certain concrete integral. And the fact that this functional indeed exists was proven by Keiki Yang, student of Webster in type A, and by Danil Kluyev in general, using abelianization approach to Coulomb branches. So here, Coulomb branch realization becomes crucial, as opposed to truncated shifted Yangian realization. And so what is the integral, how it looks like? So now we just treat this element of H, for which we're trying to take a trace of. We just treat it as function on this torus for the gauge group, and we multiply it by some additional factor, W xij ai, that is given by some quite concrete formula that you literally just read off from the data of group G and representation N. So this thing knows nothing about lambda, mu, about quiver. You literally read it off from your like theory, G and N. And how it works, so this W is the product over all roots, but now for the gauge group, for G, and then you take sinh of alpha. And then you divide it by the product over all weights of our representations of cosinh of beta. So some meromorphic function. And then you multiply it by, this is just the thing that corresponds to the grading in our trace, e to the power, maybe that's not so important, sum of ai times the sum of these x's. Any questions about this? So, and again, how the proof works, you first show that this right-hand side indeed descends to this graded trace. I mean, then you should do some analytic things, but maybe that's not so important. And then from just this general estimate that we just did, we conclude that it must be equal to this trace up to some constant. Any questions? Okay, and let me give you an example now. So if we were in type A, and if our mu was in W orbit of omega I, then actually all of this mu and Wi, lambda, they all are parameterized by Young diagrams in this case. And how it works, you draw the Young diagram, I draw this one, and then you read off the corresponding V and W just by considering not the number of boxes in these columns. So V1, you see one box here, and one box here. So V1, V3, and V4 are all 1. Then V2 is 2 because here we have 2 boxes. And W2 is 1. That's because W always captures the corner on which it stands. And then an interesting thing is that, so you have this integral presentation, and this is something that you have, but then the question, okay, can we extract something concrete out of it? And the answer is yes. You can compute this integral by residues. And so what you get when you compute this integral by residues, and again, Gayota and Okazaki, they definitely envisioned something like this. You get a very explicit formula for this trace. Namely, you see that this trace of some function R of these variables, x is the sum over so-called reverse plane partitions. This means that you just fill these boxes by numbers, and you want to have strict inequalities between these numbers. And then what you do, you just literally substitute these numbers into your R, and this is the grading part in our character. And this result, this corollary, was also obtained by Kamnitzer, Kalmykov, Leroy Pierre Pinet, not published yet, by using completely different approach, using so-called Kähler W algebras. Any questions about this?
So why Gayota was interested in a graded trace?
They were interested in partition functions of a theory. And then they realized that partition function is basically functional on this space. Right? So as we remember, as we discussed, this space, let me show it you again, is defined as the quotient like this. And this is more or less precisely this twisted trace condition. Twisted trace condition that Gayota and Okazaki consider. Just written slightly differently, like formally. Any other questions? Okay, yes. So yeah, and in particular, this implies for free that these extremal modules we care about, they have a simple spectrum, just because you see all of these eigenvalues here are they. And these modules have Gill van Zeitlin basis in particular. And we know the eigenvalues. Okay, and now let's go back to Hikita's story. So how it helps eventually. So now we know that this trace we were computing, it's some concrete sum over these reverse plane partitions, and outside of type AA, you should replace these so-called heap diagrams. That's something that people who are doing combinatorics studied a lot. So you have this sum, and you're trying to compare this trace with this vertex function. And by the very definition, this vertex function is given by some integral of some class over this moduli space of quasimaps. But then by localization theorem, you can always compute this integral by passing to fixed points of this moduli space of quasimaps. And then what it turns out that these fixed points of these quasimap spaces, they are isolated, and they are precisely in one-to-one bijection with these reverse plane partitions things. So you literally get the same sum. And you get the equality that we wanted to obtain.
How you see these inequalities looking at the set of fixed points?
Yes. Let me comment on this. So you remember that our quiver variety, MH tilde, it's just one point in this case. But this is a point that lives in fiber over 0 stable modular GV. And this point has some representative. And actually, the representative of this point is given. So the representative of this point should be like we have our space N, right? This should be some collection of maps. And the claim is that the representative of this point, let me draw it in this example, will be the following. So let's put just one-dimensional spaces everywhere. And then let's draw arrows like this. So whenever you have an inequality in this RPP, we draw arrow in the opposite direction. And we also put C here. And so now we treat this thing as a framing. This is W2. And the columns here, so V1 is 1C, V2 is C plus C. So these two C's. V3 is C, so like V1, V2, V3, and V4. And now remember, like representative of quiver variety is a bunch of maps between these VIs. So in these terms, now just like this arrow corresponds to the identity map between the corresponding one-dimensional spaces. And all of the other maps will be zero. So that's and framing goes to this guy. So this is a representative of this particular fixed point. And now you want to deal with these quasi-map spaces and take their fixed points. Then one can show that what you should do, you should now just like replace. So now you live on P1. So you should replace all of your one-dimensional spaces by line bundles on P1. So now you should put here O of D11, here O of D212. Sorry.
Yeah. Okay. So
and
you
now
get inequalities.
exactly to
Otherwise,
have a
there will
map.
be no. Yeah.
There will be no map. Yes, you want a map between these bundles that at infinity is equal to identity.
Yeah.
Yes.
It's fun.
Yes.
Yeah.
Yes. Exactly. Okay, and so now in the remaining 4 minutes, let me mention that actually we also see some interesting combinatorial things that again, as always, people who are doing combinatorics, they observed it like maybe 10 years ago. But here we sort of see some codification of this story and somehow more general. So let's see. So if we combine the results above, what we see that from one perspective, just the character of our representation that we were dealing with is given by just sum over this reverse plane partition. So I'm just substituting r equal to 1. So I'm not doing weighted sum here anymore, right? So we just do an honest character. So we get weighted sum over these RPPs. But on the other hand, as we discussed, from like purely different perspective, we computed this character by looking at the tangent space to the Coulomb range. And we got this in this case. We get the product over alpha and delta minus such that the pairing is 1 of these things. And so what we get some explicit combinatorial formula. And it's actually quite non-trivial. It's indeed known to be true for arbitrary almost dominant mu by the results of Nakada. Not sure it's published, but yeah. And now note that the right-hand side of this equality, this thing, as we discussed today, it makes a perfect sense for arbitrary mu in double orbit of lambda. We don't need to put this restriction that mu is like very close to being dominant. The only difference that appears is that like now you have some powers here. So here you just take power 1, because for almost dominant thing, it cannot happen that the pairing of alpha with mu is 2, for example, if alpha is negative. But in general, it can happen. But we do know that the character still has a very concrete and nice formula like this. So there is a natural question: how about the left-hand side? So can we say something about the left-hand side here? And we know that it should be equal to this vertex function, but still, does it have a reasonable formula? Like in this almost dominant case, it has a very nice formula using this reverse plane partition that you can work with. How about in general? I don't know the answer. So you're still integrating over the moduli space of quasi-maps. Fixed points might not be isolated in general. So it's more complicated. And maybe it still has an integral presentation, as we discussed. Again, this integral presentation, as we discussed, this integral converges precisely if mu is almost dominant, but maybe it will, instead of taking this integral, one should compute residues formally and do some renormalization. I don't know. Yes, so let me finish here. Thank you very much.
Okay, thank you very much for this nice lecture course. And by the way, don't forget to email me the updated versions, because actually on what you sent me, the last couple of
Right, right.
slides, they do
were,
not exist.
yes,
So.
that's true. Yes, yes,
All
yes.
right, now it's Q&A session. So any questions to Vasily?
Okay, I have a probably very simple question. Earlier, you gave a very simple example of Nakajima quiver variety of the cotangent bundle of P1.
Yep.
So in this
Good.
case, yes. So in this case, what the corresponding quiver is? It's just a Jordan quiver?
It's even simpler. In this case, the quiver is just 1, 2.
I see. And one is the frame.
And 2 is the framing. 2 is the framing.
Two is the frame. So basically, this is not the Jordan quiver. It's just the quiver with a single point without any loops.
But know that even in this example, what I'm trying to say is that we never make any computation for this T star P1. You always play this game that you're decomposing your quiver into two pieces. So like you can either present it as 1, 1 plus plus 0, 1, or the opposite direction, 0, 1 plus 1, 1. And Coulomb branches, so you have a map from like U of SL2 to the tensor product of two Coulomb branches, one corresponding to this thing, tensor, the one corresponding to this thing, 0, 1, and the opposite direction. This fact that we have 2 here corresponds to the fact that there are 2 irreducible objects in the category O for SL2. And then these are the building blocks. These are these extremal guys. So you can show that in this case, these guys are just differential operators on A1. So you're considering,
yeah, for Nakajima quiver variety, you will have 2 parameters. One is the framing dimension vector, and the other one is the root dimension vector. So for this T, the cotangent bundle of P1. So here you have
you mean lambda and mu?
Framing.
You mean this lambda and mu?
One is lambda and the other one is mu. That's
right. So in this example, lambda will be 2 omega 1. And mu will be 2 omega 1 minus alpha 1. That is 0.
Okay. Yeah.
And now
alpha 1 is the corresponding to one single root.
Absolutely, yes. And know that this irreducible object description that I mentioned, in this case, it just corresponds to the fact that now you can decompose 0 as omega 1 plus minus omega 1, or you can decompose it as minus omega 1 plus omega 1. And omega 1 and minus omega 1, they already live in W orbit of S2 orbit of omega 1. So what I'm trying to say that even in the case, and that will be these shifts, that will be these mu i's. And what I'm trying to say that even in the case when you're considering, maybe I should mention this, even if the case when you're considering non-shifted Yangian, it's useful to use the shifted things, especially non-dominantly shifted things, to study its representations.
And so in this case, the mu is also the extremal weights situation you
know that mu does not live in W orbit of lambda.
It's
right, because 0 definitely does not live in W orbit of 2 omega 1.
I see.
But you can decompose
this is the most I see that's a two-dimensional.
Yes, it's not a point, but you can decompose lambda as omega 1 plus omega 1, and then there are 2 ways to decompose mu. You can either do this, right, or you can do this. And now these building blocks, these guys are like this will be like your lambda 2, and this will be mu 2. And now mu 2 already lives in W orbit of lambda 2. Maybe I should also just mention that, for example, if you're in type A, then what we just discussed, So in type A, arbitrary parabolic W algebra is isomorphic to this truncated shifted Yangian. And from what we just discussed, now we know that arbitrary Verma module over the parabolic W algebra is a tensor product of these extremal modules, of these building blocks. In particular, we immediately read off the Gelfand-Zeitlin character for arbitrary Verma module over arbitrary parabolic W algebra in type A.
In the type A you just mentioned, and one of the special parabolic, maximal parabolic, the corresponding quotient is the Pn.
Exactly.
So does that give similar to this cotangent bundle on the Pn, correct?
Exactly. So this, geometrically, these objects are you take T star G mod P, it maps to the nilpotent cone, and now here you have a Slodovy slice, and you take its pre-image here as E tilde. So that's this parabolic.
Oh, that's nice. Well, thank you very much. This is really
thank you for listening.
In this direction.
Okay. Any other questions? I have sort of, but it's maybe more on the side of speculation. So, but it's motivated by this homological whole algebra perspective. So you deal with, I mean, the geometry which is behind of what you've been explaining, it's transversal slices in affine Grassmannians.
Absolutely. Yes, for
All
AD.
right. Now, and so then you see some these nice planar diagrams with Gelfand-Zeitlin inequalities. Now the question is either a two-dimensional upgrade or speculations. People try to construct two-dimensional versions of the fine Grassmannian. But the important thing is how do you look at it? As far as I know, people try to look at it from the perspective of representations of Kac-Moody rather than fine. Okay.
Great question. Let me try to answer it. I think that sort of like at the level of presentation theory, we do see everything. I mean, so let me return. Okay, that's conjecture at the moment that I formulated. But I don't think it's so. I mean, we are working on it. I think it's doable, but yeah, I don't know. But Q is arbitrary quiver. So in other words, it corresponds to arbitrary Kac-Moody group GQ, and mu is this like almost dominant thing, almost dominant. But what it actually means, sorry, yeah, that this will be slightly combinatorial. This actually means that mu, if you write it as W orbit of lambda, then this W is so-called lambda minuscule in the sense of Proctor and others, people who are doing combinatorics studied this a lot. And then whenever you have such a W, and your W doesn't have to be, you don't need to work with ADE. It's arbitrary Kac-Moody groups. You can always associate to this W an analog of this Young diagram that I wrote. This is so-called heap diagram that you should think of as follows, that you draw your quiver, it can be arbitrary, and then there is a now you start to put some balls here, and you throw balls in different order. Balls correspond to simple reflections in the decomposition of W, and then you write inequalities like this. So there is always some three-dimensional structure that you can associate to arbitrary quiver, And then this conjecture that we make is that the trace of L, I mean, that it's still true that the answer is the sum over RPP corresponding to this heap. Again, like the same formula. And on the quiver variety side, everything should still remain the same. Namely, Higgs branch is still one-dimensional. It still has one representative, and this representative precisely corresponds to like putting these arrows between these one-dimensional
Yeah,
spaces.
but probably what I'm asking it rather geometric interpretation, because you had that story with fixed points and so on, and here it's combinatorial
Absolutely.
answer, but to what question?
Absolutely, yes. But then geometric interpretation should be this work by Tomasa and Spencer Tamagni. Again, they work on this. It's not finished yet. Namely, that again, they are not restricting to ID quiver. They consider arbitrary quiver and consider some critical cohomology of this quasi-map space from P1 to this particular quiver variety, which is a point in this case. And the claim is that on this is like, as you explained last time, like using this cohomological Hall algebra story, one can construct the action of this shifted Yangian on it, and it descends to the action of the Coulomb branch.
But from kind of pure I don't know, aesthetical maybe reason, if I want to start with something which is a two-dimensional version of the affine Grassmannian.
Yes, maybe let me comment on this. About this, I don't. So maybe let me comment one thing. That's one result that I didn't mention, but we actually use it. So I told you that we computed tangent space at the fixed points of this MC. In this case, when mu is in double orbit of lambda, actually there is a very general proposition that maybe it's due to myself. That if quiver Q is AD, then this Coulomb branch MC, lambda mu, it's generalized slice in affine Grassmannian, but it always maps to the affine Grassmannian. This is an honest affine Grassmannian. There is no problem in defining it. But this map is not an embedding, in general. It's embedding only if mu is dominant. And know that if we are, for example, in this mu in double orbit of lambda situation, then it's never dominant. But then, surprisingly, the following happens. You can consider though we have an action of this torus T on this Coulomb branch, and like from the category O perspective, the relevant part of this Coulomb branch, like the part on which your category O objects will be supported, is repeller to the fixed point. Let me denote it by R lambda mu. So this is repeller to the fixed point P inside MC lambda mu. Right, so this is like some Lagrangian, some half of our Coulomb branch on which all of the objects of category O are supported if you take associated graded. And then interesting things happens. The proposition claims that after you restrict to this repeller, you are putting no conditions on lambda and mu. It becomes just isomorphic to what is known, like, let me write it, T mu intersected with Ger lambda bar here. So it's just the same, it's a repeller to the fixed point Z lambda inside Ger lambda bar. To Z mu inside Ger lambda bar. So they are also known to be MV cycles. So in other words, the Coulomb branch remembers all of these MV cycles, and and like being restricted to repellers, there is no difference between the Coulomb branch and like the affine. It's literally an embedding isomorphism to these MV cycles. And so conjecture is that, yes, we don't know how to define this double affine Grassmannian, but at least if we care about category O, it's enough to think about this repeller. So conjecturally, in general now, when Q is arbitrary quiver, then this R lambda mu inside MC lambda mu is the correct replacement, of the repeller in the affine Grassmannian of G that is not defined. And sort of like it's enough to understand.
No. Repeller in affine Grassmannian.
In affine Grassmannian of G. Yes, in the affine Grassmannian of G. Yes.
But still, it's still sort of a one-dimensional story. Yeah, I understand that MV is somehow, in general, something like semi-infinite or something.
But the point is that this thing is always... there is this paper by Vasily and Boutier that I don't understand at the moment. I want to understand it at some point.
Yeah, me too. Yeah.
But in this paper, they do work with this T mu intersected with Gr lambda without taking closure. That is important. They work with this object for arbitrary G, not necessarily finite dimensional, also for arbitrary Kac-Moody thing, and they do prove that the dimensions of these guys are a pair of rho with lambda minus mu. That is precisely 1/2 of the dimension of the Coulomb branch.
Mm-hmm.
So yeah, so and my hope here is that for example, how we compute the actually, like in this ADE story, how we compute the tangent space to this fixed point of the Coulomb branch. We use this identification, and then we work on the affine Grassmannian side. So my hope is that like these repellers, indeed, they should still be isomorphic to these objects that Vasily and Boutier define, and then it should be possible to say, for example, understand the tangent spaces at these fixed points. Because, for example, you see this conjectural formula that we have for these tangent spaces, it's very similar to, it's like, so this number, it's just like, when you computing the tangent space to the Schubert cell Gr lambda inside your affine Grassmannian. And the only difference now is that you see we have these real roots that should correspond to some like real form of this Kac-Moody group that one should consider in this story.
Yeah, maybe just one
Minimal
more thing.
form.
You have some nice combinatorial objects, some nice, I don't know, functions. What I mean, for example, instead of trying to define this 2D Grassmannian, you work with slices which somehow without existing. Okay.
That's what we
For
do
example,
at
let
the
me
moment,
ask,
yes.
if I ask a theoretical question, what will be the 2D analog of, for example, Satake correspondence and your symmetric or whatever functions and these planar diagrams, they should appear as analogs of, like theory of symmetric functions. What will it be like? What is a 2D Satake if you do not know what is a double?
As always. So I don't have an answer to this question at all, but as the only thing that I can say again is based on this identification. So there is something that you can still read off from this Coulomb branch, and that's what was proposed by Braverman, Finkelberg, and Nakajima. But you know this, yes. But that's just like
That's the point.
piece
And
of a
actually,
story.
even before Nakajima, Braverman, and Finkelberg tried to approach double affine Grassmannian.
Right.
Yeah.
Right. So maybe, yeah, their point is that, okay, we don't know about the affine Grassmannian, but we can consider top dimensional irreducible components, top dimensional of this repeller. And we do know that the vector space generated by them, if you sum over all mu, then it should be V of lambda as a representation of GQ. So that's their version of this geometric Satake. And actually, there is a very interesting question that I don't know the answer to at the moment. Namely, again, if you pass through this Hikita story, then okay, let me be really brief here because so if you just take ordinary Hikita, you take functions t, then it should be isomorphic to the cohomology of the Higgs branch mh tilde. And now if you take the direct sum of all of these functions, then we know that it should be isomorphic to the direct sum of cohomologies of mh tilde. And Nakajima explained to us overall mu, long time ago that indeed GQ acts on this space, and if you take here the top component, then this will literally be this V of lambda. So this tells us that we do have this object on the left-hand side given by Hikita, but the question is how to embed inside of it the direct sum of irreducible objects of this R lambda mu. So this is already a question that happens purely on the Coulomb side. You have like two different, and this basically this space can be also identified with the direct sum of these like hyperbolic restrictions of IC shifts to the fixed point. So in other words, you have two ways to measure singularity at your fixed point, and you want to compare them.
Is there a problem with IC shifts? Because it's kind of, you do not take closure, you said.
We do.
Okay.
Yes. We do. Sorry. Yes. You see, we have it here. Yes.
Yeah. All right. Well, very interesting, and probably we should kind of wrap it up because now
Absolutely,
it becomes
yes.
a personal discussion. All right, Vasily, thank you very much. It's very exciting and a lot of questions, and I remind you about updated notes. Please don't forget to send it. And thanks again for your lectures. Well, and this is it.
Thank you very much for the invitation. It was a great pleasure for me and a great experience, actually. Yes. Thank you.
Thank you. Okay, bye.